That's okay? This sign is important when trying to solve and using loop analysis. Okay? So the loop direction is important. If the loop going in the same direction, the current will naturally flow in. For example, the loop going from negative to positive, then E positive. If the loop going from positive to negative, then this EMF will be negative, right? If the loop going in the same direction, current flowing in, right? If the loop going with current, it means that it will be positive, and so on, right? So I remember that, right? Right? One more thing that we have to squeeze in electricity, we have to remember resistance in series and parallel and thing, right? Write this down. Right? No. Let's share the
I'm now going up like a minute after they equalize.
Right, so I just going up for people online, right? Right? Huh? No, I tell them. It's not live. It's private now. Let's send it for them. Right? I will send it for them. Gotta get data we can do about some of this. Right? We gotta get data we can do about module one, even if it's online, right? Wait. Huh? Another rubber top. I just keep going it over. Right, so current is this, charge is this. These are all the formulas for electricity, right? We need to remember the difference between PD and EMF. For PD is the same definition except the energy is converted from electrical to other forms. EMF, the energy is converted from chemical to electrical. This is the relationship between EMF, internal resistance, and terminal PD. Right? Please remember, when the circuit open, what you're reading. If the circuit open and I put a voltmeter here, what you're reading? You're reading the EMF. So that's the relationship here. It's drift velocity. That's the average velocity that these electrons will move with. Right? And it's called a charge density. This is the formula here. These are all the little circuits for a metallic conductor, a filament lamp, a diode, and a negative coefficient thermistor. Right? And here we have Kirchhoff laws. Kirchhoff's first law and second law. First law, sum of all the currents is zero about any junction. Current entering, you current leaving. Alright? Here is your second law. The sum of all the EMFs is equal to the sum of I by R. Right? We need to remember when the loop, these arrows here for the loop. These arrows here for the loop, right? These arrows here for the loop. When the loop is going the same direction, current will flow out of the battery, positive. The loop going against how current will flow in battery, negative. And next way to figure it out, if you're going from negative to positive, E is positive. If you're going from positive to negative, E is negative. Loop analysis here, right? If the loop in the same direction, current flowing through the resistor, positive terminal PD. Here, otherwise, negative terminal PD. All right? So you need to remember that. Last thing you need to remember is whenever you have resistance in series and parallel, how they behave in a circuit and how they behave otherwise, right? Huh? I just squeeze in loop. That's from the loop. Okay? That's from the loop. What I was saying, huh? Right, nice. If I gave you two resistors in series, you need to remember the formula. Resistances R1 plus R2. If I give you two resistors in parallel or more, and you have to be able to prove that, right? And in order to prove it, you use these rules here, right? series, parallel. In order to prove it, you're going to use these rules here. Series, parallel, this is resistance, current, voltage. But you need to remember the rules when you're proving it. So in series is R1 plus R2. Here will be 1 on RS, 1 on R1 plus, 1 on R2. Current in series is the same. Current in parallel splits up. Voltage in series is splits up. And voltage in parallel is the same. Alright? So you have to remember these laws when proving this. So to prove this, you're using this. To prove this, you're using this rule. To prove this one, you're using current splits up. This one. Okay? To start the proof here, always remember you're starting here, right? V is equal to V1 plus V2. To start the proof here, you are using current splits up. Alright? Last thing that I want you to remember is the potential divider. If I give you a voltage, right? The potential divider allows us to divide the voltage, right? So if I connect a voltmeter, right? If I connect a voltmeter here, that voltmeter will read a fraction of the whole circuit. This is called a potential divider circuit, right? V1 will be V, a fraction of that V. So that'll be R1 over R1 plus R2. You all might remember it from a circuit like this as well. Here was 10 volts and here was 8. Yeah, inside it. So you can explain that? With some bridge? Yeah. No, this. Oh, this formula represents the fraction of the resistor, right? I can prove it for you fast. All right, anyway, so whenever you have two resistors in series, right, voltage splits up. So the fraction that this voltage represents is this formula here. Is the fraction of the original voltage that will give you V1. So if it was here, yeah. If it was for here, like V2, V2 will be V by, now R2 becomes the value on top. Huh? A profit. Right? So if you have I here, you gotta remember that V is equal to total voltage here will be equal to the current in the circuit by the total resistance. What's up? Right? And so that means I is equal to V over R1 plus R2. Right? That's I, right? So what will V1 be? V1 will be the current in the circuit by R1. Right? So if I is this, you'll get V over R1 plus R2 by R1. Right? And then you can factor out the V and you'll get R1 over. Right? You might remember something called a potentiometer, where we have an entire wire that the length varies in resistance. Right? So a potentiometer is where instead of the resistors, you have a long wire. Right? And what you could do along that wire is by altering the position, you alter the resistance, and it could operate just like this. Right? I just want to show you the Wheatstone bridge, right? Ready? I'll take another rest. Alright, so watch here. Right? So if you look here, here we have an example of a weak stone bridge, right? Four resistors connected just like a direct bridge, right? And the weak stone bridge is said to be useful or balanced whenever the galvanometer reading is 0. So when the galvanometer reading is 0, the weak stone bridge is said to be balanced, right? What that means is that there is no deflection here. So it means that the potential at A is equal to the potential at B. So if both potentials equal, what does that mean? No current will flow, right? So nice. So all we have to do is find the potential at B, find the potential at A, and we're good to go. All right. Let us see current flowing here, right? Current will split up. Let's call here I1. Current will split up here I2. Right? So I2 will flow here. I1 will come here, and I1 will flow here, right? You okay with that? Nice. So how do we find the potential? What's that? How do we find the potential at P? The potential at P should be I1 by P. That's P, right? That should be I1 by P. And the potential at A, I2 by R. at A, yeah. That's I2 by the resistor there. Right? I can do the same thing here as well. The potential at P here will be I1Q, and here will be what? I2S. If I divide them, what I'll end up with? P on Q is equal to R on S. So here's the use of a Wheatstone bridge. Here's the use of a Wheatstone bridge, right? If I have 1, 2, 3 resistors, if I know 1, 2, 3, and I can find Q, provided balance, right? Suppose suppose I want to find Q. One of the ways I could do it is I could alter one of them, like for a rheostat or something, and alter this resistance until the G value is 0. When I get G is 0 now, I could come to the Wheatstone bridge formula and solve for anything I want. Right? So basically the Wheatstone bridge will compare these resistance here. Right? And if one unknown, I could find for that. Alright? So that's one of the applications of the Wheatstone bridge. Alright, so that is electricity. Let's do a couple questions on that now. The problem is how going on. But they have the years, right?
Just stuff that's like 3 minutes. 22. Let's go.
Right, 2024 is magnets, right? So we need to know that, right?
Yeah. No, I don't know if you know what something last I don't have?
Yeah, all good stuff. We are for that time. For that time.
Yeah.
For that time.
But that's something, right? We got it. So now on the silence, please.
Hey, nothing ain't going. Take what I come. For that real time.
Nah, we will leave already. Hey, good signals.
All right. I don't know how can share it, but 2022. Let's try 2022 number 1 now. Anybody remember the year which had the drip velocity in it? And number 2? And number 2? And number 2? And number 2. So we go back and do that, right?
Now we know 1 or 2. No, we don't have this signal. We can't go through the
So I am on. One thing for just you are cool stuff, right? But again, should have 2022 number 1, right? And then we're going back and do some of the pieces of number 2 that had drip velocity and thing.
Wait, the number 1 or number 2?
1.
Number 2, how about drip velocity?
Right, in the space below, draw a circuit diagram showing three resistors in series. On the diagram, label the voltages and current associated with each resistor. Right, and I think they asked me to prove it after something. Yeah, and then prove it after, right? And then we'll go to that circuit there and find IL and thing, right? Then we have a graph to draw. Right, so your question could look something like this or one with capacitance, right? That's what your question could look like for you. One like this or one with capacitance. Right, the first one is to put the circuit, three resistors in series. And the current through all is I, right? Current through all is I. Okay? So they want you to place in series, connect it to a power supply on your diagram, label the voltages and currents, right? Nice. They want you to derive the formula for effective resistance after. So we know that V is equal to the total voltage here, V is equal to V1 plus V2 plus V3. Right? So remember that V is equal to IR, right? So the total current by the total resistance is equal to V1 is I by R1 because they all have the same current. I by R2, I by R3. That's okay? So it's this plus this plus this. Right? And then you can divide everything by I, and you will get R1 plus R2 plus. In this? No. Use the diagram in A part 1 and the other formula. No, you don't need no purchase law. Right? And thing like you don't need purchase law. You might need it. You might need it here. Although you don't have to apply purchase law here, right? Right? Do you have to apply purchase law in next one? Huh?
Yeah, but
Could you just simplify the distances
yeah.
and simplify the circuit a little bit, right? So you don't necessarily have to, but I want to use purchase law.
Make it simplify too.
Right? So they want you to find IL. Right? They would like you to find the current through RL. Try quick now. So that we end up using the same values, right? Put I1 here and put I2 here. Right? What could be the loops that you could use?
Yeah, me.
Huh?
Left second, right second.
So we could use one here and one for the whole thing. Right? Because there's no voltage here. Right? So you'll get nothing in that circuit.
Well, the field only that's so. I mean, that's because what is here, right?
Yeah, but then that's not good to second row.
Or the first or school store, we have to connect yes, yeah. Like if we now read from the current.
But try to answer now. So apply Kirchhoff's law in the first loop and second. Oh, sorry. The voltage is 9 volts, right? Try it quick. Right? So you can use the same loops I have, right? Loop 1 and loop 2. So that we will end up with the same thing, right? And then solve. Yeah, I'm going to show you. The various variable resistors. Also, we don't need. Okay. Sorry. We don't need to do all this. IL is what? 30 ohm. Anyway, we'll go ahead and do it. So you see, what we could really do now is just simplify this circuit and just see how the currents split up here, right? But as a practice, we'll do some loop analysis, right? So loop one go in the direction that current will flow in, right? Minus the plus. So that's positive 9, right? So loop 1 will be positive 9 is equal to loop 1 going in the same direction as I1. So that's 5I1, right? Loop 1 going in the same direction as IL. So that'll be plus 30IL. Loop 1 current will come back down here and go this way, right? So the loop going with 2.5. So that's plus 2.5 I1. Right? I1 flowing here and here. So it's going with the current here, with the IL here, and with the I1 here. So you end up with this. So you end up with 9 by 7.5 I1 plus 30 IL. All right, that's one thing that you could do. What about loop 2, Azaria? What will you get? It will be 9 is equal to. Oh, I say add back up, you do all one time. Okay, yeah, that's good. 7.5 I1 and then 5, 10, 15. Well, I use I2 here. So that'll be 30 I2 and then, right, we don't need this because this is not in our loop. We're going this way. Right, so that'll be 5 and 2.5, that's 7.5, 5, 10, 15, that's 30. Hmm? How about get it plus 30 here? Oh, 5, 10, 15. Add it up one time. Remember from Kirchhoff's first law, what do we know? Current entering the loop I1 plus I2 is equal to IL. So I can take off IL here. I can take off IL here. And I will get 7.5 I1 plus 30 by I1 plus I2. So what we will get, 30 plus 7.5 is 37.5 I1 plus 30 I2 equal to 9. I could bring these two together and solve them simultaneously. Yeah, man, that will cancel off nice. So 9 minus 9 is 0. 7.5 minus 7.5. 37.5 minus 7.5 is 30. Someone wrong? Again, I1 as 0. Am I get I1 as 0?
This, they tell me to put the I2 going this way also.
I don't know.
That's way.
But you get value for I1. What do you get for I1?
2. 2 I.
2.
Yeah.
Yeah, it don't matter. Just the signs would have been different. So let me see if I make a mistake with my signs then. Hold on, right? If I make a mistake with my signs. So I'll go in with the arrow here. The first one, right, for sure. I did the first one, right? The second one, Azaria did. That's how we wired wrong. Yeah. I2 going this way. So I'm going against the arrow. So this should be minus. Right? Using my convention. Huh? Yeah, that'll be loop 2. Oh, sorry. Right, yeah, because the way I put I2 here, current entering is yours current leaving. I put my I2 going in the opposite direction. So when my loop going this way, current going next way. So it's going against I2. Right?
So how come you pay a loop like that? Why we can't put one loop on one side?
You can pay loop however you want. I just fixing it based on my diagram.
In this case,
Because you see the reason why I'm maybe getting a mistake is because I use my loops like this. Right? I use my currents like this. So probably that's why I'm making.
Like, if we can put loop 2 in this other side, this is.
Huh?
Like the other side, this is stuff.
You can put loop 2 here.
Yeah.
Try to see with the workout. There's no need to put a loop here because there's no EMF. Right? Kirchhoff's second law deals with EMF and PDs. Alright? So I just fixing back this here, right? So this is my equation 2. This is my equation 1, right? This was correct because I did this. Sorry, I set them up here. So that's 9 to the 7.5 I1 plus 30 I2. Alright, so let me see if add it. This is 0. I got 18 18 is equal to 7.5 plus 7.3, 7.5 is how much? How much? 45 I1. So I1 is 18 over 45. The question didn't ask for that. Huh? I just worked it out. So that will help me find IL. So I2 is what? I2 is equal to, plug it in here now. Tell me what you get. I2 will be 9 minus 37.5 by 18 and 45 all over 30. How much you get for this? I2. Negative? Negative 0. Sure, right? Put this whole in the calculator. Negative 0.2. Huh? Oh, you just drop this on this in the calculator. All right. Right, so IL, so right, so like somebody go show me the current direction. I just get the current direction now, right? And the signs show it. The current direction should have been the other way, right? But nothing wrong with that. It will still give you the same answers. All this means is that I put the current direction in the wrong direction, right? If you had put it the other way, you would have gotten 0.28 for I2. So IL will be I1 plus I2. I1 is 18 on 45 minus 0.2. How much is that?
Everyone 2/5.
So that'll be 0.2.
Final answer?
Yeah.
This was negative 0.2, right? Are you sure?
Negative, this was
0.4? So as we apply Kirchhoff's law, right? Right. What would have happened if we did it like this? That we practicing, right? 9 volts. What would have happened if we simplify this circuit like this? What would happen if I attempted to do this circuit like this instead? So watch it here, right? These two combine into 7.5, right? And then it's splitting up here and here. So it means that these two in parallel for this one. See that? 7.5 in parallel with the 30 and the 30 and 30, right? What would have happened here? You would have recognized that current going to split up evenly here. And so could we have found current in the whole circuit? Yeah? Could we have found current in the whole circuit? Yeah. We could have, right? We know the voltage is 9. Let's see if we can find the total resistance. These two in parallel. These two in parallel, so that's 1 on 30 plus 1 on 30, which is 2 on 30. When you flip it over, you'll get 15. So these two are 15 ohms. 15 plus 7.5 is 20, 22.5. Right? So the total current flowing in the circuit is 9 over 20.5, which is 0.4 amps. So therefore, If the whole thing is 0.4, current will split up here, 0.2i, 0.2, right? So really actually this circuit wasn't designed to use Kirchhoff's law. It was designed to do that. It was too simple to Kirchhoff's law, right?
That's not a point five again, right? So that
would have been this plus this.
So that's a parallel.
No, these two in series. When the current reach here, right, it will split back up, right? And then it will join back here. No, because this in parallel with all of this. When the current leaf here is splitting up here and here, right?
Yeah.
So it means that whatever happening here is in parallel here. So these two in parallel. I can put these two together because the same current flowing here and here. So that's how I get it 7.5. So this 7.5 in parallel with both 30s. Right? So you can also do the circuit like this. Alright, let's check on the next part now. That's quality. Alright, that's not. Alright, that's not. Alright, huh? No, yeah, break over there.
Outside.
Outside?
Google Play or drawing from the school. No. This one. And I like on one side, we have 50. We're going to take one. They're going to show you the combination. They come with everything.
I think that's
That's 4.
It's like 15 versus 1.
Seven pluses.
all right, next. Right next you have the interval.
Yeah.
Real boring. All right, next part is the graph, right? Next part is the graph, draw a straight line and so on, right? After the graph, that's it? Wait, no. Yeah, 2022 have it. So a small cylinder made up N-type of a diameter 4 and length 1 carries the same current in device A. What was the current in device A? Same here, number 2. Same here, number 2.
The current is root 2 and 2. No, 0.5. 0.5. No, this is 0.5 amperes.
Oh, yeah.
Right, so I'm just going to read over the stuff we have here and we can try it, right?
I0 is 0.5 amperes.
So the electrical device, the rating is 0.5 amperes, right?
You want I0 or I3? That's it.
Huh?
You want I0 or I?
We will need I.
I, but I is root 2 and 2. Sine 105.
Right, so
Now we gotta use
we found the IRMS, right? What was the IRMS value? That's the RMS, but that's the peak value. So remember I told you, what did I tell you 0.5 amperes was? That was the RMS value, right? So when they quote something, they will give you the equivalent, the DC equivalent of the AC. So that 0.5 is the RMS value, and I showed you how to find the peak value to get the formula, right? Yeah. So the RMS value is 0.5 amperes. Any calculation you're doing with DC, this is what you need. Right, the question also gave you the diameter, which is 4 by 10 to the minus 3 meters. The question gave you the length, which is 1 centimeter. Same number 2. Same question, number 2, part C. Yeah, remember what? We did A and B already. Huh? Oh, alright. Okay. Part C we doing, right?
And give it 3 by 10 to the minus 3.
Right? And then they said the number density n is equal to 3 by 10 to the 17. That's centimeters cube.
So we got a multiply 10 to the power 6 minus 6.
So I just convert centimeter to the minus 3 to meter. Or you can work everything in centimeters, up to you.
We have multiply 10 to the power minus 6.
Right? Because I remember writing the velocity here as centimeters per second. Yeah, so you can leave it in centimeters. Right? You can work everything in centimeters.
So then we had to convert the
Right, so if you want, how you convert this to meter cube? What does this say? What is saying? This saying that it has 3 by 10 to the 17 electrons in a particular volume in 1 cm cube. So if you have 3 by 10 to the 17 in 1 cm cube, how much you will have in 1 meter cube? Multiplied by 100 3 times, right? Multiply by 100 3 times, which is 10 to the 6. So that will be what? What do you mean? By 23, right?
No, I say no centimeters, yeah, minus.
Huh?
Centimeters, so we 10 to the power 11. You got a minus in the others.
No. What does this here say?
Per centimeter.
Right. This says per centimeter. So this is saying 3 by 10 to the 17 and 1 cm cube. Right? So in 1 meter cube, it should have more, right? Right. So if I convert this to meter cube, it will be 3 by 10 to the m to the minus 3. All the minus saying is per meter cube. All right? Now they want you to find maximum drift velocity. Ah well, I just don't support Luca now. Basketball. You know Luca? From Real too?
Yeah.
I support Luca now.
No, we have to go by the final.
Every man back. What is
26.
26?
Luca. We can't do it. We can't do it.
Right, so we need to find the maximum drift velocity. How are we doing that?
I think we subject B because I have an
Laughing at my meal. Right, what I again? I is 0.5.
No, I thought I 0.
I is 0.5. N is 3 by 10 to the 23. A is what? A is the area, right? So we still have to work out pi r squared. So it's pi by, so I divide this, right? So 2 by 10 to the minus 3 squared. Let's put it straight in the calculator. If you end up with something more than 10 to the 8 somehow, right? Shut the door, yeah? Sorry, you're wrong. Sorry, I said that to the room. Somebody forward that to me now. That's telling somebody. You're too fast. Did I make a mistake? Already my Alright, there you go. Oh, what y'all got? Point 8 0.83. Anybody else got that? Ariane? You got that? Alright, let's go again. No, it's RM or something. What happened there? No. Right, let's go again. That was 2022. 2024's Magnet. 2023 was 2023 was what again? Number one. 2023 with the dates already. Oh, are we not done? Sorry. Oh, sorry, 22 and next part. Right, state how the drift velocity in C part 1 could compare to the drift velocity in copper of identical dimensions with the same current. What would happen? What would the drift velocity be? Smaller? Why? Copper is a better conductor, right? Right, so what will happen is that, remember inside there you have your, right, so because it's so fast, they will undergo collisions, lose energy and move slower, right? Alright, and the last part is to use the resistivity formula, right? Resistivity is, right? You can do the last part from part 3. Part 3, resistivity will be your RA all over L. The R value that they gave you was 80. Right? We will tell the area here, and the length they gave us is 1 by 10 to the minus 2. Ohm per meter. Ohm meter, not ohm per meter, ohm meter. Right, the SI unit is ohm meter, right? Ohm meter. So resistivity. right? And we did 2021 yesterday, right? We did 2021 yesterday. Right, before we do a run through on magnets, let's check out 19.
What's the year?
Get it. I didn't write it. No man. Here, let's see man. 5 hours, good. Right, 2019 number 2 part B has a Wheatstone bridge. Let's just take a look at that now. There's a Wheatstone bridge in 2019 number 2 part B. 2019 number 2 part B. Well, y'all think it makes sense? Well, y'all finishing crash courses now, right? Y'all think it makes sense to be doing past papers in the crash course or do like new questions? Right? No, but y'all have to switch them. Suppose I'm provided with all the solutions to past papers. New questions better, right? So someone. Huh? Yeah, come like normal and do the questions and correct. No? I will give you all the words. That you will have solutions already now. So you're not ready. You're remembering more than those.
So we can write people like that. You give the questions that actually come.
Yeah.
What's that?
For the all-nighter, those questions you would not have seen them before, right? So don't come and ask me the years,
Yeah,
right?
but that questions are coming.
Huh?
That questions are coming.
I wish. No, I just do them. I don't do them. I don't do that. Huh? No, I see it.
You wait.
I just do like a few hours. You get one? I have to see, I just do them. So I have them videos, but I don't have them. So what the girl doing for me, she going back over and she going back on the money. You don't have it. She just do back on the money. She send it to the customer and she will do a PDF for you. She will finish by hopefully the next week. All right, let's check out the Wheatstone now. Show that the grid is balanced when that happened. 2019, number 2. Hit a book. Come on, do this one. You run. Million, okay? 2019, number 2, part 3.
Yes.
No, like the screen itself. What was the guess? Derive an expression for the math. Yeah, this out from here. Where you go? Oh, okay. Yes, you start from here, and then make this up. Get all right? All right, let's see how you reach Stonebridge work. Everybody can look at it. Huh? No. Everybody can look at it. Everybody have a question to look at or choice on the board?
Try to report.
2019, number 2 start B. Ah, yeah. Well, no, you're not using the formula. You gotta prove it back. You gotta prove it back. You have to cut somebody who has the answer. Come on the board, look it up. Like that. Come on the board and explain.
Saturday night box tomorrow.
Right, so we have to prove that RL on R3 is equal to R1 on R2. Same thing we now prove, right? You all see that?
Yeah.
Same thing? And when I come and do it without the notes? Want to come and try?
Yeah,
I'll give it this here.
give away.
Everything in his pocket. Everything in his pocket. You want to try? Eight times two, yeah, I'll go back. So tomorrow, right? Right, so tomorrow I'll give you a series of questions, right? So you're done with that. Right, and I'm spending much time on mom. That's good. Huh? Yeah, I'm gonna go on.
Somebody say it.
Huh? Again, like two questions, I'm sure. I'll spend more time on that one. Guys, ready? Right, how are we doing this? Who want to try it fast? Banaya? Or try it fast? Very good, Banaya. Huh? Di ba madagang kinaraba? Wait. Alright, so we're trying to prove the part on top, right? Wait, no. Alright, so you had to prove that. Right, so you had to prove that. I was just trying to show you where you should end up with.
Wait, no.
Right, so no, that's not what you have to do. What you have to do is like what I did on the board. Show that for the circuit for the Wheatstone bridge it balanced, the galvanometer reading is 0. So you have to go back and find the potential here and work out the whole thing and show that this will happen. More than that. Who want to try? One did earlier. Who want to try? Anybody want to try? I'm not trying now. Who want to try? Come fast now, I want to go through Magnus with you. Huh? It's not proof there. R1, R2, R3, RL. So I'll start here. When the galvanometer reading is 0. Come now. Try to come fast now. Come fast.
So that would be
So first thing you gotta tell them to balance the potential at x and y equal. Potential at x. You gotta tell them that the potential at x. Potential at x equals to
so then is that it?
right for the whole world now potential at x equals to potential at y.
All them do is play with physics.
It's
I1,
come twice.
I1, R3.
So I1 get up put in I1 I right.
Two nine.
Yes, like put in where I1 is. Yeah, I'm putting I2.
Oh shit.
Why put plus? So you just find IR3 equals to I2R.
And that's divided by I1.
Let's make R something.
Alright, hold on.
Sorry. Right, so the same proof again, right?
Shit.
I'm really doing good here. We are not there. Right, so we did all the questions, right? All in number one, some 2024, 2020, 2019, just 2019. All right. Let's talk about some madness now. I mean, I'm charged.
Oh, just fix up this guy.
Fix D. That's what I mean? I know he cancel.
So wala kang magkaibahan na wala mang correct.
No, I changed that. You will want that. All right, so magnets, right? Let's run through magnets. All right, so we need to remember a few things, right? In a magnet, as a north and a south pole, magnetic fields go into the north and leave the south. That's okay, right? And also, if I give you a current carrying conductor, there's also a magnetic field around it. Around the current carrying conductor, the magnetic field, how do we work out the direction of the magnetic field? Right? We use right hand grip rule, right? 1, 2, 3, 4, your thumb, right? Your fingers point in the direction of the magnetic field, and the thumb points in the direction of the current. So therefore, circle means what? In or out? Out, right? So therefore, magnetic fields going in a anti-clockwise direction. That's okay? What would happen now if I take a magnetic field, right? And I place a current carrying conductor in it. These two magnetic fields will interact. Correct? And it will experience a force given by what? An experience of force given by Fleming's left-hand rule. So Fleming's left-hand rule, thumb, first finger, middle finger. Your first finger is the force. That's what you're trying to find. Your first finger is your magnetic field, and your middle finger is the current direction. So current coming out, magnetic field going north to south. So the force is where? The force is upward. That's okay? Right? Magnetic field north to south. Dot means out. So my middle finger pointed out of the whiteboard. So my thumb pointing upwards. That's okay? So the force acting upwards. Yeah? Emiliano? Right? So what's it here, right? So you have your current magnetic field force. You're trying to find this. Magnetic field going north to south. My first finger pointing north to south. Middle finger showing current direction. Dot means out. So my middle finger pointing out. And the thumb pointing upwards. That's okay? Right? So therefore, the force is upwards. Alright? That force now is dependent on what? That force is dependent on the strength of the magnetic field. Right? Remember how the field lines look? The field lines build up underneath and push it upwards. Right? So therefore, this force is dependent on the strength of the magnetic field, the current flowing in here, how long the conductor is, and the angle. Right? The angle is the angle between the conductor and the field. And its maximum when is what? 90 degrees. 90 degrees, right? So B is equal to F over I L sine theta. right? Maximum is maximum when theta is equal to 90 degrees. Everybody okay with that? Right? So those are the things that control the force exerted on a conductor. Alright? Huh? Dot is out. Yeah, dot is out, X is in. Right? Dot is out, X is in. Huh? The force on the conductor. Right? So if you have a conductor in a magnetic field, that's the force on it. Right? Remember what's the SI unit for magnetic field strength? Tesla, right? So this is magnetic flux density. And the SI unit is Tesla. What would have happened now? What would have happened now if you have a charged particle? Let's say you have a charged particle moving through a magnetic field. Will it experience a force? Yes. And the force is BQ, that's the charge, by the velocity it's moving with, right? By sine of the angle between them, right? Again, the force is maximum when what? Theta is 90. Okay? So all these things control the force. So for example, since that charged particle, let me just show it a little different. Since that charged particle is experiencing a force, right? How will it move in the magnetic field? It'll experience a force like this, right? And go down, right? And you'll recognize if it stays in the magnetic field long enough, it can follow a circular path. So it can constantly be acted on by the forces. All right. So we need to remember how to find that force and how to apply it, right? Which one? Right. So as the particle moves, right? As the particle moves in there, right? If you remember, by the way, how you find directional force? Right. Left hand rule, right? So according to left hand rule, if I have current moving in a magnetic field, I'll get a force. That's okay? Right hand is generator. If you want to find current. Left hand is to find force, motor rule. Right? Right. If you have a current carrying conductor in a magnetic field, you'll get a force. Current carrying conductor is a positive charge, right? So if you have a positive charge going this way, you can have a negative charge going the next way. So let's assume the charge positive. Magnetic field is what? There's a positive charge, right? So the positive charge going towards me, this will experience a force. As the force acts on it, its path will begin to curve. Right? If it stays in there long enough, it could cause it to create a kind of circular path. Right? And the force exerted on the charge is given by this. Right? The force is max when theta is 90. Everybody okay with that? So the force exerted is given by that. We need to be able to find the magnetic field strength in different conditions. Right? How you find the magnetic field strength? Let's say you have a straight conductor carrying current I, and you want to find the magnetic flux density here. How you find it? Right. Yeah. What's the formula? Right. It'll be mu naught. That's the permittivity of the substance here over I. That's the current flowing all over 2 pi by the perpendicular distance. Let's call that E. That's to find the magnetic flux density at distance A away from a straight conductor. Right? Huh? Right. And then if you have a flat coil, it will be mu naught n I, and the number of turns all over 2 by r. R is the radius, right? R is the radius. And n is the number of turns. And then you have it for a solenoid. Right? How, besides a formula, right? Besides a formula, how do we find, what are some of the techniques that we could use to find B? We have two main things that we could do. We could use a Hall probe, and the Hall probe operates on what? Called PD, right? You remember how to find Hall PD? Hall PD is what? Huh? Something over net, yes. What over net? VP?
Yeah.
Oh yeah, try that quickly. Yeah.
BH. BH is equal to B over I.
Huh? It's BI, right? So it's BI over NET.
Wait, I thought that was just something. I thought that's something.
No, NET. And the next technique that you can use is something called the current balance. Right? Current balance basically is something like this. Simple diagram here. If you have the weight mg and you place a current carrying conductor in a magnetic field, it will experience a force. Right? So the way the current balance works is that the force, which is the magnetic force, is equal to mg. And I showed you how to find the magnetic force, right? So that will be, I'll write it here for you. That would be BIL is equal to mg, provided that theta is 90 degrees. All right? So these are the little things that you need to remember, right? These are the two ways to find flux density, right, using experiments, and these are the ways to find flux density using, actual values, right? From current in a straight conductor, circular coil, solenoid, and these are the ways to find it.
Everything is about electromagnetic induction. Faraday is like differentiation.
Right? You have to remember how to, you also have to remember how to explain a motor, how it is work. Still, no, it's not about idea.
Yes, is equal to
Right? And then we need to remember in electromagnetic induction, right? Yeah, and transformers, yeah. Right? You need to remember electromagnetic induction, which incorporates two laws, right? If I take a magnet now and I try to move the magnet in and out of here, what's happen? Right? That's Lenz's law. Faraday's law says that if I take a magnetic field, right, and I move the magnet in and out of here, the magnetic field will cut the field lines, right? And Faraday said that the EMF induced is proportional to the rate at which we cut something called, remember what it is? Huh? Magnetic flux linkage. Very good. Magnetic flux linkage. right? Flux, magnetic flux is B by A, and N by this is magnetic flux link.
Any formula for this? Any kind of the raw formula?
Huh?
Any kind of the raw formula?
Well, I have an explosion.
Energy is equal to K, or is equal to K by D over D magnetic flux.
K, but yeah, when you remove this.
Whenever we get magnetic
So
flux.
when you reach here, right? So I want you to remember, right, that the faster you move it, this saying that the faster you move the magnetic field in the coils, the bigger is the EMF value. But what did Lenz say? Lenz said that it always opposes motion, right? So for example, when the magnet moving in, this will induce current so that it will oppose motion. So when the magnet moving in, it will push it out. So here will be a node. Okay? So when the node trying to go in there, it will push it out. So here will be a node pole. You can use the right hand grip rule and work out current direction. Current will flow enough. Current will flow like this. So in order to include Lenz's law in this formula, the power minus sign. Okay? Anybody remember the next version of this? Have a next version of this.
BVL.
Huh? BVL. BL. And last thing you have to remember is transformers.
BS is more than VP.
Right? So you have your number of coils in your primary, number of coils in the secondary, voltage in primary, voltage in.
Is equal to omega BAN sinus omega D.
Right. What you say? In a transformer, right? Remember, a transformer works on the principle of electromagnetic induction, right? So in a transformer, you need to remember that this ratio is always true. Number of coils in the primary over number of coils in the secondary is equal to VP and PS. Right? If this bigger than this is a step down, if this smaller than this is a step up. Right? And this formula works. But remember, if you were to write in IS on IP, it only holds if the transformer is what?
Step up.
Ideal. Right? So instead of writing it in here, I gave it this version instead. Power output is equal to power input by the efficiency. So if the efficiency is 100, output equal to input, and you're good to go. If the efficiency is 75, 75 and 100 by the input will give you the output. And then you can go and solve current. Remember that power is equal to what? I by V, right? So you can find current. So the only time that the formula IS and IP holds is if the transformer is ideal. Yeah? It don't matter. Same ratio. It don't matter. NS on NP is VS on VP. Right? Same ratio. But just remember these two signs are opposite. Right. So sometimes the transformer is not efficient. If the transformer is not efficient, you can use this formula here. If it's 100% efficient, then output equal to input. But if the transformer is 75% efficient, then 75 over 100 by the input will give you this. Alright, so I just gave it this version because this doesn't always work. Right? If it's not ideal, you can't use this. You gotta come up with something else, right? Right? I know I'm tired, but I just want to run through 2024 number 1. Alright, so let's go through it, right? So what is flux density? Basically, you can take that formula there and put it in words. Right? V is equal to F over IL sine theta. Put that in words, right? That's the flux density. Draw a label diagram to illustrate the direction of the force acting on a straight conductor in a uniform magnetic field. What are you talking about there? Draw a fully labeled diagram to illustrate direction of the force acting on a straight conductor of length L carrying current I at theta to the uniform magnetic field. What diagram is that? It's on the board. Well, technically, it's on the board. Huh? That's Fleming's left-hand rule, but which diagram it is?
The one right here, A and B and I.
Right? What? This one here. Draw a fully labeled diagram to illustrate direction of the force. So they want you to use this on Fleming's left-hand rule. You have the magnetic field, current carrying conductor. Dot shows what? The direction the current moving in, right? Huh? Yeah, you can do it like that. Yeah. Right? So part 1 can work like that. Part 2, write an expression for the force per unit length in terms of BIL. What will that be? F is equal to BIL sine theta. A 3.5 so far, that is 2, 6, and 2, 10 marks, right? Are you okay with that? A 3.5 meter long wire carries a current of 7.5 amperes, making an angle of 30 degrees with a uniform magnetic field strength. Calculate the force. What's the formula we're using in part 3 there? Chibish, what formula we're using in part 3 there? Right, we're using the same formula. F is equal to VIL sine theta, right? Work it out, please. Vinay, we'll work it out some more again. Plug in the values, please. Everybody watching in 1, right? Everybody watching in 2024? Who do have it? Everybody have it? Plug in your values now. Just be careful. Remember that your magnetic your P value is 2 by 10 to the minus 3. Calculator, no, put it in degrees. And next thing, make sure you calculate in degrees when you're.
Everything is degrees now.
You know, 2 years. Nothing right then.
I don't think so because even though I got
Yeah, simple number. Alright, yeah, then nothing there. Just pay attention. Once you put in degrees, make sure you calculate in degrees. Well, the person tell you in radio. Huh? Yeah. Just look at the question. If you say degrees, make sure you calculate in degrees. How much you all got for part 2? Part 3?
0.02625.
Right, so again, for those who lost, are using this here, right? B is 2 by 10 to the minus 3, I is 7.5, L is 3.5, and theta is 30. Figure 1 shows the section of a current carrying conductor of uniform cross section. Right? Figure 1 sketch the pattern of the magnetic field around the conductor. Which law is I still on the board? Which one? Right hand grip rule, right? How will it look? How will it look? Clockwise or anti-clockwise? Anti-clockwise, yeah. Right? So it will be anti-clockwise. You okay with that? So you're drawing circles here, anti-clockwise. Right, you're using this one, right? Right hand grip rule. You have to draw it. Watch it here. Watch it here. You're drawing it here. No, not like that.
Like this.
Next one. An electron travels at 2.5 by 10 to the 7, right? So they give you an electron, they give you the velocity. So write it down, they give you the velocity, 2.5 by 10 to the 7. Same question, right? That is, I'm not seeing the letter. Everybody okay with that? So they give you the velocity and movement with perpendicular to a magnetic field. So it looks like what? What it looks like? This one here, right? An electron moving in a magnetic field. So they gave us the velocity, they gave us the strength, and they told us theta is what? 90, right? And Q is what? Q is an electron. Everybody okay with that? So part 1 is determine the expression for the magnitude of the force. What will that be, Shivish? F is equal to what? Huh? BQV sine theta. Part 2, right, I like this part here. I'll get to show you. Huh? Part 2, the electron will travel in a circular path. Determine an expression for this part. So watch this here. Oh no. That's a sign. Where I do a few more. Right, so watch this here. F is equal to BQV. Theta is equal to 90, right? So that's the formula there. B is what? They gave us B, 10 by 10 to the minus 3. All right, let me do substitutors here. Right, question. What provides the circular motion? What provides the centripetal force? And this here? Yeah? Yeah? What provides, what causes it to turn? The magnetic force, right? So centripetal force is BQV. How you find centripetal force again? mv squared over r. Right? And they want us to do what? Make r the subject, right? So this view cancel here, bring the r here, you'll get mv over. Are you okay with that? And then plug it in and tell me what you get for R. WhatsApp this number 329. Solve for R in the meantime, please. Solve for R in the meantime. 200. Right, solve for R in the meantime. Right, so what you all got for R? Remember, it's the mass of an electron, right? It's an electron, right? So mass of an electron by the speed it's moving over 10 by 10 to the minus 3 over the charge. How much you got? 0.014. Anybody else got that? Anybody else got that? 0.014. Trouble? Are you sure? Yeah, you can work it out to plug in the values. Yeah? So you plug in M, mass of the electron. Mass of the electron is 9.11 by 10 to the minus 31. The speed is 2.5 by 10 to the 7 all over 10 by 10 to the minus 3, and Q is 1.6 by 10 to the minus 19, and they got 0.014. Nice little question, right? Next, state lenses law, and you are provided with a bar magnet and galvanometer. Look at right here to demonstrate lenses law. That's okay? So you're doing the same thing here. All right, so tomorrow we just do questions. So tomorrow we just do some questions I've put together, and then just in case I'm late, I'll make somebody come and go through the solution tutorial, right? Just in case. I don't think so. I'll be back by sure. I missed all it. Right, but I still give the question away to you and stuff.